Okay, so we were looking at different types of voltage sources, and we looked into how these voltage sources are important in maintaining the levels of voltages, and what kind of applications that need constant voltage sources. Now let us take an example of let's say a DC motor. Okay, so if I have to rotate it at a constant amount of time, okay, then we need a constant voltage source. So I can probably use a technique called pulse width modulation. Okay, this concepts will be coming up in your analog communication. Okay, analog communication and digital communication in your upcoming semesters. So there's a concept called PWM, right? Pulse width modulation, where it needs constant voltages. So accordingly, the width of the pulse remains constant, and when the width of the pulse remains constant, so we can have the DC motors to be constant. Okay, so we are actually looking at the pulses. Okay, so let me just draw a pulse here. Okay, so you can notice that your pulse, the first pulse, okay, is actually not that thick, right? The width is less, but the second one, the width is high. So which means what you're able to see here is the width of this pulse is able to vary. So because of this variable uh, width in pulse, okay, the voltages also does change. Okay, fine. So in order to have this constant width of the pulse, I need something called constant voltage source. So in that case, what is going to happen is, you can utilize these kind of circuits, right? These kind of circuits where this will actually enable us in having a constant voltage source. So now if you compare the next one, right? So if you compare, the width of this one, okay, the width of this pulse, this is actually higher, right? So which means I am giving an extra voltage, and the width of this pulse has increased. So you will be learning exclusively about these concepts in your communication subjects, right? Okay, fine. So we have seen this voltage source, right? As to how the Zener diode plays an important role, and how or why we are using these BJT circuits, and we have R2, R3, and RL, right? So BJT is very much good, in having the load driving capability, right? The load driving capability of BJTs are much higher, right? So up till this point, we had discussed, and today we'll just look at an example, okay? And design example. All of you can be ready with your calculator, pen, and notebooks, right? So we need to design. Did we actually look into this example, students? Did we see this example in the previous class? Yes, no? I somehow feel that we have done this already. Can you also give me some inputs? We did it, right?
Yes, sir.
Yeah. So using these circuits, we also designed. So one thing we kept in mind was, the Zener voltage will be exactly half. So 9 volt was given, so we used 4.5 volts, right? And ultimately we even designed R1. Okay, I2 was taken much larger than the base, so 500 nano into 100, so that gives us 50 micro, and then we calculated R2, and then we calculated R3. Okay, so taking this tolerance into consideration, this 10% tolerance, right? So higher resistor value and lower resistor value. So you can see plus 10 is actually giving me about 85. Okay, and minus 10 is giving me about 77. So we can either use 68 K, or as usual we can use another 10K in series if I want the exact 77 kilo ohms. Fine. Okay, and ultimately the currents also were looked into. So you can see that the IC max is greater than 18 millivolts, and VCE max, that is the voltage between the collector and the emitter of this base, is actually greater than 12 volts. Okay. So if we now look at the computer analysis, right, we have solved the problem, right? And if we look at this analysis, now let us just compare few values, right? We have the output voltage at about 9 volts, right? Yes, 9 volts. That is what is specified. And VZ is taken as 4.5. It is divided by 2. So in your computer analysis also, you have 9 volts here. And RL is about 500. Fine. So figure shows the results of graphical analysis of circuit designed in the example. So whatever circuit that we have designed here or developed in this example, the same thing was simulated in the computer. Now keep in mind, students, right, whenever we design a circuit, it's always better to actually first get into the simulation, so that I get to know how much of outputs I'm going to get, and what kind of levels that I need to give for my voltages. Should I really increase or should I decrease the resistance values? All this can be done, right? So it is pretty easier when you try to simulate and get things done, rather than actually hooking up the circuit and trying to remove the resistor and then reconnect the resistor, right? So all this becomes a very tedious job, right? So that's the reason we always have the simulations. Now many IC designs that you see also has the same kind of technology, right? So before they get into production, okay, so what they do is they simulate things, and they find out if their designs are good. If it's good, then yes, it's continued. If it's not, then they get back to their drawing rooms, to their circuit rooms, and then they try to redesign things. Okay, fine. So this is about how design is actually performed using computer analysis. Now it is seen that when Zener voltage is 10% higher than the specified 4.3 volts, R4 moving contact set to the top gives about 9 volts output. So when it's at the top of R4, right? So it's very interesting here, right? So you can just observe this section here. Okay, this wire is connected to the top of R4. Okay, I hope you're able to locate it, right? So the top of R4. So when this is connected to top of R4, we are getting about 9 volts. So when VZ is 10% lower, so which means I have to connect it below. So you can see here, it is connected below. And what is the voltage level? We are getting about 11.68, right? So we need approximately about 12. So we are getting 11.68. So by the adjustment, okay, just because of the adjustment of this wire, this wire exactly, this wire, so we are able to change the values, okay, change the values of the output potential, right? The adjustment of potentiometer, which is R4, the output can be set to the design 9 level voltage, 9 voltage level, regardless of actual Zener voltage within the plus or minus 10% tolerance. Now, sometimes what happens, the impact of Zener diode, in order to counterattack the impact of this Zener diode, which is about plus or minus 10%, what we do is we have this kind of potentiometer setup. So if I can vary the values, okay, if I can change the wire connecting at the bottom and to the top of R4, then what happens is, I can actually nullify the effects of D1. Okay, so this to be remembered. So if I can have this, then of course I can neglect the effect of D1, and ultimately, this potentiometer, the wire setup here will actually help us in nullifying the odds that are going to have with the circuit output. So any doubts here, students, as to why we are setting this up and how to nullify the errors and how to tolerate the values of the diode, the Zener diode D? Any doubts here? Yeah, students, any doubts? Is it all fine?
Yes, sir.
Yeah. Okay. So ultimately, you should understand if in case something is not something is actually impacting, something is not supporting a circuit. When I say not supporting, it means if whatever the designed value, okay, I should be able to achieve them. If I'm not able to achieve these kind of values, okay, then what I'll do is I will try to make a counter attack to the disturbances caused by this device. Okay, I wouldn't say disturbances, the effects of these devices. In this case, we have the Zener diode D1. So what I'm going to do, I'm going to just put a potentiometer here connecting R4 at the bottom and top. So in this way, I am able to vary the values or change the values of my output from 9 to approximately 12 volts, right? So this is the idea of any circuit design, right? So anything that you design should ultimately be able to satisfy the specifications. You can just recall, right? If you go to your um, stores, let's say to buy a computer or a laptop, right, the first thing that you will have in mind is what kind of processor that you are looking into. Isn't it right? Yes or no? Don't you
Yes, sir.
think of what kind of processor that you need? You will,
Yeah.
right? So once you're satisfied with the processor, then probably you will look at what kind of graphics can I include. Can I make it still stronger by having a graphic card? Maybe maybe a higher spec graphic card. So once you are fine with that, then you might think, can I have a larger screen? Or maybe right now you might be using about 13 inch. You might want to have a larger screen, so you might opt for a 15.6 or 17 and a half, something like that. So you have a specification in mind, and you're planning, or you're trying to match up that specification. Similarly, when we design any circuit for that matter, right, we think of, first we design, or we have a draft that my circuit is going to give me this much of output. Okay, so without this much of output, I am not going to accept it. If it's not giving me that output, then I am going to make some changes, just like how we saw for this potentiometer setup, and I will make sure that this design works out as per the specification. So ultimately, it's all about maintaining the levels of specs. Okay, so I hope this point is clear. So can we move on to the next concept?
Yes, sir. Yes.
Okay, fine. So now we'll be looking at current sources. So we have seen voltage sources, right? And we have seen the importance of these. And as I've mentioned previously, current sources are nothing but those which can enable or help us in having constant values of currents at the output. Okay, no matter what, I need to have constant currents. How do I achieve it? Fine. So now let's look at the circuit here. Okay, it's almost pretty same. We are having an op-amp and we are having a BJT setup. Always keep in mind, whenever we are thinking of load, the capability of carrying a load, then I am looking at BJTs alone. There's nothing that matches BJT's performance in with respect to load carrying, with respect to current handling capabilities. Okay, fine. So I make a combination here along with my op-amp and BJT. Okay, so I power up the BJT, I give plus VCC. Now remember why we are using this plus VCC to negative or the ground terminal. Can someone tell me why is that? Suppose I connect a minus VE, then what happens? We have discussed this, right, in a previous class.
Virtual.
Suppose I need a negative output, then I'm going to connect a minus VE here. Suppose I need a positive outcome, okay, then I will have a plus VCC here. So we are always looking at the positive outcome, right? Okay, so now let us discuss the circuit in detail. A current source, I think all of you know this, right? In my introductory class for this module, I have specified as to what is a current source, what is a voltage source, right? In short, I've given you all the definitions. So taking that forward, a current source is a circuit that supplies constant output current. Now, having a constant output current is important here. It supplies a constant output current. There could be few appliances. Okay, let us say, for example, voltage stabilizers. The stabilizers that you use for your electronic equipments, they do not need any spikes, right? They do not need any current spikes or voltage spikes, but they need constant outputs, right? So that you can think of that as an example. In turn, it is actually securing your gadgets, your electronic items, right? So that's the importance. Thus, current flows in the conventional direction. So out of the positive terminal of the current source. Always keep in mind, okay, it is from the higher potential to the lower potential, okay, and current flows from the positive terminal. A current sink also has a constant current level, but the current flows into the terminal of the current sink. So it's a reverse, right? You are sourcing here, but then in sink, okay, you are actually doing the opposite. You're not actually getting a constant current. A current source circuit with a floating, when I say floating, it means that it is not connected to ground. Okay, so with a floating load resistor RL, so we have this RL, and this load is actually not connected to the ground, but then it is connected via R1. So I can say that this becomes a virtual ground here, okay, which means it is passing through R1 and then R1 is getting connected. The circuit functions like a non-inverting amplifier. Okay, why is it non-inverting? Because I have my plus terminal here. Okay, and this is acting as good as a feedback loop, right? So let me just so this one, you can see that it is acting like a feedback loop. Fine. Okay, so the circuit functions like a non-inverting amplifier with V1, okay, with V1 appearing across R1. So whatever is the voltage that I'm giving here, the input voltage, I term it as V1. This will actually appear at R1 here, okay, R1, because whatever is my input, the same thing is across my output, right? So which means this is held at constant, and whatever is here is getting mirrored. So you should understand, when I say it's a mirror, which means it's an exact replica of this voltage that is given here. The same thing will be appearing across resistor R1. Okay, so this mirroring concept is very important. V1 appearing across R1. Okay, so the load current is always, okay, so I can say that it is IL, load current, is equal to V1 by R1. So whatever is my resistor, that is R1, okay, and the voltage across R1. So ultimately you know that it is your IL. Right. So this is independent. Of course, what I have done is I have included some extra information here so that it can serve as your notes. Okay. So what I'm doing is this particular point is actually extra, which is actually needed for your understanding also. But then if you have to just stick to the circuit mode operation, then you can actually start your explanation from here. Okay. Nevertheless, we will learn it in detail and we will try and understand the concepts, right? So this is independent of the load resistance variation. So if in case any change in my load, okay, any change in my load resistance, okay, it's not going to hamper. See, because you can see that my IL, okay, this IL is dependent on resistor R1. Very strange, right? Usually we used to have V1 by RL, but then here it's not at all dependent on RL, but then it's dependent on R1. Okay, so this is interesting. So this is interesting so that even if there is a variation in RL, doesn't matter. I am going to have the same constant load current. Okay, so this is independent of load resistance variations as long as the total voltage drop across R1 and RL does not exceed the out voltage. Okay, so this drop across R1 and RL should not actually exceed the output voltage. So whatever is here, okay, this drop across R1 and RL should be less. So it's obvious, right? So if in case there's a lot of drop occurring at these resistances, of course it's going to impact my output, right? So drops are always to be expected or to be made as low as possible, right? So only then this will work out. Okay, only then this concept will work out. Okay, and as long as the BJT has sufficient collector emitter voltage to keep it operational. Okay, so collector and emitter voltage, okay, we should make sure that this potential is actually constant. If maximum load current is less than 25 milliamps, so let us say now we had assumed that it is going to give us about 25 milliamps, right, previously in the previous lectures. So if the maximum load current is less than this value, 25 milliamps, the BJT may not be required. So you are using BJT. So if you in mind, traveling at about 60 to 80 kilometers, and is it worth buying a Bugatti Veyron, students?
Yes, sir.
I don't think so, right? So if you're planning to move at a lower speed, there's no point in buying a high spec car, right? So similarly,
Yes.
if my output, okay, if my output here is going to be less than 25 milliamps, right, I do not want this high performing device here. I do not want to include this BJT here, but instead what I will do is I will try to somehow manage only with my op-amp and resistors and capacitors, right? I will try to play around with only these devices. Okay, so you should understand here that if you want something greater than or equal to 25 milliamps, then that is when you are employing your BJTs. Reference voltage V1 can be derived from a voltage divider or from a Zener diode. So this V1, for this V1, actually I can connect using my voltage divider. So what's a voltage divider? I'm giving 18 volts, then it gets divided so into +9 and -9. So that is this V1 that we are talking about. So additionally, you can have some voltage divider circuit here, and from there it passes to the op-amp. Okay. The circuit can also be described as voltage to current converter. Very interesting, right? How circuits can change their properties and actually work as converters, right? So I can call this as a voltage to current converter. Why is it so? Because you can see that I'm giving V1 as my voltage input, right? And what is my output? I'm going to get a current output. So current is in the form of IL. Now IL is again dependent on R1 but not RL, interestingly. right? So I can say that, it is a voltage to current converter. Any doubts here, students? Can I proceed? Is it fine? Any doubts here?
Yes.
Please feel free to ask. So understanding, how the circuit works, and making it, making it reach or meet your specifications is a very important factor ultimately, right? So as I mentioned, right, if you want to make your circuit economical, and you're actually operating below 25 milliamps, then maybe you can eliminate this and directly connect the output here to the resistor RL. Fine. Okay. So you should be very careful in designing your circuit. You can actually change, or you can actually control how your circuit is going to be, is it going to cost high or is it going to cost low? Okay, so all this to be kept in mind. Fine. So the next, that we'll be looking into is, a different circuit here. Remember, that was a floating ground, and then here I have, directly connected to the ground. So you can see the difference here. So I have actually moved up R1. Okay, R1 was actually present in this point here, but then this is actually moved up here. Okay, and I'm going to make some changes. So V1 remains as usual here, right? V1 is there, and I have inverted the terminals here. Plus is coming here and minus at the top, right? Plus is VCC and minus, that should be minus with the base current, okay? So this becomes important here. Fine. So let us look into the circuit. In the figure, right, we see that V1 is the voltage between VCC and the op-amp non-inverting input terminal. So you can see that, I have my V1 here, okay, and between the non-inverting and VCC. So, at this point, okay, this point. So here I'm going to give my V1. Fine. The PNP, okay, PNP junction. I think you would have heard of this PNP and PN, right, with these junctions. So the PNP BJT emitter. So you can see that this is a feedback here, right? So the emitter is connected here to the minus terminal, so that the circuit behaves as voltage follower with V1. So what is a voltage follower, students? It's not a new concept. What's a voltage follower?
Output follows the input.
Yes, whatever is at the input, the same thing you will obtain at the output. So we can say that the output is following the input, right? Okay. So this is appearing across resistor R1. Now, this R1, is actually playing a very important role in, controlling the values of currents, and, making sure that these levels are constant. Okay, so R1 is very important here. So the constant input voltage maintains BJT emitter and collector current constant. So emitter, okay, the emitter currents and the collector currents. So these are to be made constant. Okay, so this is enabled by the usage of R1. Okay, by the usage of R1. So whenever we design, okay, we have to make sure that the value of R1 is selected appropriately. Okay, so the current source circuit, so this is the grounded load. Okay, so that's one important change that we are looking into here. For, the load current level is set by the voltage drop across R1. So whatever is the drop across R1, okay, so that is actually impacting the load current. Now you might ask, sir, how is it impacting? That is because, it is connected to the BJT here, right? So it is controlling the current levels at BJT. So ultimately my load, okay, my load is exactly, let me just erase this. Yeah. So my load, is exactly IE minus IB, IE minus IB. So if I'm looking at this formula, then IE is actually controlled by R1, right? So ultimately, because of that, my base current also does change. So I can say that, R1 is the master here. Okay, resistor R1 is the master here. As I change the values of R1, my output currents also does change. Okay. Any doubts here? Any doubts here, students? Can I proceed?
Yes, sir.
Yes,
Okay.
sir.
Okay, thank you.